Okay, I have 4 o'clock right now. I have 4 o'clock right now if you want to start.
Okay, so hi, I'm Steve. I'm going to be describing a few things I've done to process data in parallel and how Raku makes it a lot easier now. So the case I'm going to be showing you, there's a file called nr.gz that's published from NCBI, and it's supposed to be a list of non-redundant amino acid sequences for everything known. So instead of showing you sequences by thing, it shows you all the things that have one sequence in it. And the sequencers are supposed to be unique. So it's about a 123/8 of a terabyte with a lot of sequences in it. The sequences themselves, some of them are tiny. Great, cat. I've got a peanut gallery here. And just to give you an idea of the size, just catting it can take an hour and change. So the question is it really unique? NCBI doesn't always have perfect quality control, and there are times when they will duplicate some of the sequences. And if you're loading all of this into a database and it's wrong, it's a real hassle. So doing the QA on it is just sort of a hobby of mine. These guys have learned to dislike email from me. But the problem is you've got that much data that's that variable. How do you actually validate the uniqueness? I mean, it starts as blast format, which looks like greater thans followed by a header line. And the header line can be a megabyte as long as it ends in the first new line. Then it gets sequences and another header. End of file ends the last sequence. So there's no real marker for end. To compare all of these, I got to filter out the headings. I then extract the sequences. If I wanted to compare them, yeah, that's only this many pairs for an upper triangular. And at a kilohertz, call it a million years. That might not be fast enough to keep up with the release cycle from NCBI. So I had to figure out a better way. One thing everyone's thinking, yeah, that's easy. You don't compare all the sequences, you SHA them, and all the SHAs will work it out. And the problem is that SHA 512 with salt using multiples stacked has hundreds of collisions. The problem is the data is so low entropy because you're using an entire byte to store 20 items. There's so much similarity in it that it doesn't really work very well for digesting it. There's no way to just use digest and compare them. So what I end up having to do is extract sequences, and I generate two files. One has got lengths and digests, and then I've got a record number with the sequence. I can sort merge the length numbers, find the duplicates in there, which is a small enough pool that I can then go back and compare the sequences. So this is what I'm actually doing. Now I'm reading this stuff. The input stream, because it's a variable sized record, there's no good way to do that in parallel. What I end up doing is extracting the sequences and then processing them in parallel and passing them off to worker threads. And everyone here has used thread pools, right? I guess we can't all raise our hand, but who really enjoys fork execs? You get to fork, and if it's not, and if it isn't, and then you got the process communication, you got to exchange the data, you got to deal with the data types, you got to deal with all of the semaphores to make sure that everything gets locked, you got to put it all back in order, you got to spit it out, you got to decide. Nobody wants this. And Raku is very good at ending your pain. So the first thing is we've all written something that starts at 0, increments, and every time you go through a loop, you print the count. And you've always said, gee, maybe it's locked up. I don't know. I haven't seen a count in a while. Everyone wants that little instant gratification of seeing the count show up on the screen. Now I could just add a loop, sleep 5 seconds and show me the count. But that doesn't do much for my program because then all it's going to do is report every 5 seconds. This is as much as it takes to start a new thread, looping, sleeping every 5 seconds and showing me the count. So Raku makes this a lot easier. We're done here. I mean, this is the core of it. If I want to have a generic writer thread, we've all had, again, the fork exec that opens standard in for gzip and writes out a bunch of gzipped output to a file. I can do that here with a proc async. And I take gzip. This here runs a gzip. I can open an output file. Here's where I bind the standard out, and then I start it. No forks, no execs, no funny logic. If I want to read from input, this is what I usually end up doing, because most of the time when you're reading input, you're going to read it in a block. So with run, that's going to create a thread running an external program, which then the colon out says I want to capture its standard output. The dot out returns me that file handle, which I then map onto input. So now I've got an input file handle that's available inside the block. The neat thing about with is it works sort of like else, but it examines undef. So as I map this, I can have an else that says, this is why I failed. So the logic is pretty clean. I'll show a complete program later. So I've got to read the sequences. Now, the easy way to do it would have been read line with an end of record equal to a greater than. And unfortunately, that's broken in Raku. I get misaligned reads after 20 to 70 meg every time. So I had to convert to fixed size reads. To do that, I do a read into a buffer. And what I keep doing is looking for, I'm treating these greater thans as if they were terminators. I find a chunk or I find no input. At that point, each time I read one of these, a read returns in Raku a blob. You have to decode it to make it a string. Thankfully, these are ASCII, so there's almost no processing on them. There's a balance in threading between the size of what I do and its speed and the number of threads. If what I do takes too long, threads sit idle. If it takes too little time, I can't feed them enough. So 1 meg reads with about a 16 meg chunk of data turned out to be right for the threading. The last thing I had to deal with on this end was the fact that my individual chunks don't end on records. So I've read all this stuff in. I know there's a greater than. I've got to store it for reuse. So this is the core of what I have that is going to be threaded for reading. Now I have to process the chunks. And one approach is a channel, which you've got a bunch of subscribers writing, a bunch of subscribers reading, everything goes through it, everything's kept in order. It's beautiful. There's a really nice description of it. The Raku.org doc site is excellent. The people that have worked on this thing, they deserve a beer from all of us. It's wonderful. Problem is it doesn't work. It's way too slow for what I'm doing. It's really designed to keep a lot of things in sync with multiple people going in, multiple processes going out, and it does too much bookkeeping. What I found is Dr. Seuss. I went back to the first grade. So I've got a gather and a take to do the reading in a lazy loop with a map and erase. Everyone turn their mics on. Just let's say it, gather and take. No, okay, well, so the trick here is a gather and take, replace the found. Everyone's done this. You create an array and you push onto it, and you push another one. And every time you push it, and then you go and you gather handles a block, and whatever is taken inside of the block, the gather returns. 1 thing, 10 things, 100 things. Gather just deals with it. So all of that variable and is it in scope and out of scope and when it just vanished. So a simple handler to read all of these chunks that I just shown you is here. I have a gather of a loop. Each time I have a chunk or I'm finished, that exits the loop. For each one of these, I take it. Now, again, inside of this block, I could modify things. I could have 5 different takes. I could have the switch from hell deciding what to take. But any take that's called in this block is output by that gather, which the problem is I don't want all of it. I don't want a piece of it. I only need one of these at a time. So I can make that gather lazy. And a lazy gather generates nothing when I assign it. All it is a promise that the next time you ask for something out of that array, the gather is going to be called to populate it. So what happens is now my gather is called on demand, and it feeds that array with whatever I want to take out of it. But until you ask for it, the array doesn't exist. So now I can take this lazy array that didn't fill up any memory yet, and I can put it into a map, which thankfully you don't have to stand on the ceiling to read maps anymore. So I'm pushing all the content of this array through the map. The thing is, I want to do it in parallel. All of the bookkeeping for handling dispatching threads, putting things out, getting them back, getting them in order, tracking everything is in Hyper. Hyper modifies the map, not the array. So basically, Hyper sucks up the map and says, I'm going to run this n-way threads parallel. That's this degree down here. The batch says, well, $_ you might want one of them. You might want to accumulate $10 underscores and pass all of them as a list into process chunk. In my case, one at a time is fine, but I can choose the degree of parallelization that it has. At that point, the Hyper and map thread things for me. Notice you haven't seen a fork, you haven't seen a semaphore, you haven't seen blocking, you haven't seen anything about who's doing what in any order. It just happens. The problem is Hyper wastes a lot of time because the size of the blocks that I'm dealing with vary enormously. The headers, some of the short sequences are used in a million different species. The long ones might be used by 10. So the amount of data in one chunk varies so much that if I wait to get them all done in order, I'm wasting a lot of time. I don't care about the order. So I can replace the Hyper with this race. And what race will do is the first time it sees any thread complete, it'll feed it with a new $_ underscore. So as often as threads are completing, I'm going back into that lazy gather. I'm having it do one more loop. It's doing whatever takes it has, and I'm pushing that out. If I take 5 things, I don't have to run the loop as often, but I'm only going into that loop when this race thinks a thread needs a new $_ underscore. Now, the chunked input, again, is where the laziness comes in. The laziness isn't in the map, and it's not really in the gather. You can think of the laziness attached to this thing. So $_ underscore is coming out of chunked input on demand. A sync is avoids having to deal with the output of the map. So what happens if you think there's, a bad habit some people had in Perl 5 was using a map to iterate a list instead of a for loop, because then you have to deal with all the expected output. Map is the same way. The only reason I'm using a map here is that race. I want the race to parallelize my map for me. By putting a sync in here, I tell it ignore any output from process chunk. So the map is returning nothing, at which point I don't have to buffer output I'm never going to read. In fact, you think about it, chunked input's going to be populated by this gather. I'm going to be filling in an array that has 1/8 of a terabyte worth, 1/8 of a bazillion. Why? I'm never going to use them. As soon as they're read, they're done. So another trick is by using \chunked input instead of the array, I dodge the container. At that point, I have a sigilless indicate. You see down below, chunked input doesn't have an @ sign in front of it anymore. What I've done is create a containerless object that is my laziness. So I've got this promise to produce lazy output from the gather without having to store it. Combine that with sync, and I have no extra storage for this. So I'm getting away from this with no overhead pretty much. The race does all my parallelization. The map reads the stuff, and chunk input deals with staging the data. So this is all it takes to have a single stream processing n-way parallel threads in Raku for output. One nice thing about when I go into the processor, there's a dollar thread. The star twidgel are the things that are created automatically for you by Raku. %*env is the environment. Every thread has its own thread object, which gives me an ID, which is nice if you want to generate output files per thread or have file handles or any data that each thread wants to keep track of on its own. So what I do here, the thing that's dispatched by the map calls thread to ID, and it stores a file handle for each thread. And that saves me some system overhead. I don't have to open new files each time. I can just keep reusing them. By scoping the files array within the input, whenever that block is exited, all the files are just closed. So there's another thing that's built into Raku called atomic int, which is amazing. This thing, when you use it, it glows in the dark. If you got a bunch of these going, you look inside the computer, you can see this funny glow. No one believes me. Okay. The great thing about it really is it's implemented in assembly so that operations on it don't require external synchronization. They synchronize themselves. So this operation atomic ink fetch, it can be run in all of my threads at once, and they won't step on each other. Before I showed you how to write that little watchdog loop, this start loop, all it does is print out the number of sequences that have been processed as they're being written out. Very low overhead, but it gives me the instant gratification of knowing that it all isn't locked up waiting for something. And the whole thing just takes a couple of lines of code to do safely. Again, without semaphores, without locking. That atomic ink fetch, if 18 of these threads call it at the same instant, because it's an atomic operation at the hardware level, they don't step on each other. They just do successive increments. So the point is, to get this done really doesn't take very much. The gather and take acquire data. The lazy loop iterates the input, and by using the lazy with the gather, allows me to stage the data in the stream. And the race allows me to parallelize the map in one step. I didn't have to create a thread. You didn't see any logic in here for creating a thread, operating a thread, stopping one, starting one, synchronizing one, testing whether the output was in the right or wrong order, detecting whether they exited. There were no catch blocks, no try blocks, no thread didn't read things properly values. It all just happened, which is the beautiful thing about Raku. The important stuff really is there under the hood. Here's some really good examples of documentation. And what I was going to do now, if people aren't asleep, is go over here. And if I've done this correctly, you can actually see a copy of this running. And I can warn you, there's one minor problem in Raku. There are memory leaks. This thing started out at 2 gig not long ago. So the complete code for processing this is right here. The interesting thing about it, that with run goes from here to there. And even with Berkeley braces and comments, it's 120 lines. There are a couple of atomic ints for keeping track of things. At the start, I loop. One neat thing, I don't know if people have seen also, if I have a quote and I have curly braces inside of it, that indicates code that's being run inside of the quote. So instead of having to have a bunch of variables or a printf, I can just stick curly braces and do the division and integerize it right there in the quotes. You can abuse it, but it's nice for output. The read a chunk is right here. This is the thing I showed you. Until I can find something, keep going. I up a number of chairs. Every so often, I dump some status information and then store the next. Processing a chunk, really isn't very long. I read it, I keep walking down it, finding the index down here of a new line and a greater than, and process what's in between. Here is the entire code to parallelize everything above this. It's a lazy gather and erase with a map. When it actually runs, and it takes a while to shut down. I've been running this for a while now. It takes a while to shut down because there are enough threads that have to be tied up. But what I said before, there's the trick of using an array to store individual file handles. You'll see here in some output, if I'm hoping people can see this on the screen, someone warn me if it's too small, but you'll see all these opens, and you'll see it's opening 9A, B, C. These are the thread numbers that Moore is using. What that tells me is there were probably about 8 threads out there doing something before it actually got into that race. And you'll see there's 5 chunks, 9 chunks, 13. In a sec, we'll get to the point where it's opened 42 chunks. The 42 threads will all have opened a file handle, and we're just going to see the watchdog running. And we're just about there. And you can see here, this is that status report. And now we're done opening new files. Every time it gets a new chunk, all of these things are running out here. You see there's only 37 chunks. And I can tell they're all running because the fans have gone up about 2 octaves. But now you see 40 chunks, 43 chunks. This is that 5-second timer catching those atomic variables. They've been incremented. But I'm not opening new file handles because the array is already populated. If you look at this thing running, you can see it's 4.8 gig right now. And here's the gotcha, 5.5. This will keep growing the entire time it runs. About the time it's finished, I mean, right now, XZCAT's in the 80%, 85%. That's pretty good with just having to pipe output. This will actually get to around 200 gig. And it will exhaust about half of my swap. But fortunately, I've got a memory that I can get away with it. The warning is if you're doing this, you've got to be careful because there still are some memory leaks in Raku. If anyone anywhere knows anyone trying to fix those memory leaks, I'll be more than happy to try anything here to fix them. And we're up to 78 chunks. I've gone through 1 million sequences now. I get that, well, 5-second gratification at least. And you can see here, these are the files it's creating. And the files at the beginning, the earliest threads have been run through a few times. The later ones haven't had a chance to catch up as much. And I've gone through about 2 million rows. So there are about 2 million sequences in here. 2,700,000. So it chews through pretty quickly. And you can see here again, we've gone through 2 million, 109 chunks. Again, these lines here are this watchdog that was just a start loop. Display the contents of these atomic ints. And they actually kind of do glow in the dark. It's fun. And that was about it. I wanted to try and show people the code. If anyone had questions about it or what it looks like when it's running, we obviously have time. Holy cow, it's a lot faster than I ever thought I'd be. I don't know if anyone wants to ask questions or I've just managed to put you to sleep. Somewhere here is my talk, right? There we go. And that was it.
I have a question.
That went a lot faster than I thought. I can barely hear you. I don't know if that's my fault or yours.
Can you hear me? Yeah.
Now I can hear you better. Yeah.
Okay. I'm trying to use supply, the class supply.
Yeah.
And is it like this?
No, it's the exact opposite. With the supply and the channel approach, there is a bookkeeper in the middle, and you have things writing into a channel and the supply takes care of putting them in order and making sure that everyone gets everything once. And if somebody doesn't get it, it retransmits it to the next one. It's a really nice thing.
Okay,
but it's a lot slower. If you've got a single thread reading the content, feeding it out to a pool of workers that process it, the lazy loop with a gather and take and a race or a hyper with a map is less overhead and runs a lot faster. And frankly, I don't think it's any more code. When you use the supplies, you end up having to have all of the try and catch for end of supply. You know, there's no more data left and all the rest of it. And by the time you're done writing all of the input and output catch try organization, I actually thought it looked cleaner the way I did it.
Uh-huh.
But then I've got one advantage. I've got only one thread reading the content. If I've got Nginx supplying 14 web servers and the back end of this is a worker pool of things that look things up in the database and feed it back to them, this wouldn't work. This is about crunching through data quickly, if you see the distinction. The supplies actually, there they are, variables.
I liked it because it looked very clean to me.
Yeah, this is what you have. You got the supply and you emit something and you have a tap method that has these things on it and it just works.
Yeah.
It is nice. And like I said, the only problem I found for it is that the amount of overhead that makes it simple and clean to use, because it does so much bookkeeping, ended up leaving the whole thing too slow for what I was doing.
Okay.
If you've seen any of the stuff I've done, it's about crunching a whole lot of data. It's not about elegantly dealing with events as they arrive.
Mm-hmm.
But is this the place you were looking to see about it before?
Yes, yes.
There is if you look in the language, tutorials, concurrency. Have you read this yet?
No.
That is the one that's in my talk. I actually gave somebody something useful today.
Okay.
This shows you different approaches.
Uh-huh.
Including the promise, and I tried just about all of these. And this is supplies, an asynchronous data streaming mechanism. A supply, if you use it, looks sort of like this. Here it is. So you have something like this. You've got a loop that catches closed or other errors and then does a receive.
Uh-huh.
And then I can take a channel, and if I have this new channel, I can create a number of processes that write the stuff and then send something to each. I can do a channel to send, and because each of these guys has attached to the channel, when I do a send on it, each one of them will get it. They won't all. It'll be sent to each one of them. That's cute because I could have 14 things taking input. I could have a bunch of these things on the output, and I could be feeding all kinds of stuff from all kinds of places into whatever backend thing is available. Because I have the channel, anyone can do a send on it. It doesn't need to be just one at a time. And the supplies look like that. Like I said, the problem for me was they just weren't fast enough.
Okay, thanks.
Did that help at all?
Oh yeah, I'll read up on this stuff now.
Yeah, if you go back in the slides, there's
Yep.
At the end here was the low level stuff, but right, oh come on, there, language concurrency. Once I put this, just look that up.
Okay.
Raku.org is the place to go. Look in those tutorials.
Yeah.
The tutorials are really nice reading. The people who've dealt with the docs.raku.org did an amazing job. I mean, I'm sure they didn't write every one of the tutorials, but collecting them, putting them in place, making sure they're clickable, readable, complete. It's wonderful.
Mm-hmm.
So I would start there. Anyone else awake? Anyone have a heartbeat?
There's 3 people with questions in the
Sure.
participant list.
Where do I go to see the bloody chat?
There's a chat and there's also a participant list. I can.
Yeah, I just don't see the damn thing.
For me, it's on the
The
bottom.
teeny tiny. I click the middle one. I see me. I click the bigger one. I see even more of me. Ugh.
No, there should be at the bottom. There should be.
Bottom, I see.
Icons.
When I do the one with the 4 things on it, all I see is. Oh, guys, just unmute yourself and scream.
I have. Hi, this is Bruce. First,
Hello.
My daughter's sleeping.
for the record, you've got 54 people.
Oh God.
And the question is, earlier you were saying the failure of using a new line as a delimiter. That happened at about, did you say 70 gig or 70 meg?
70 meg, 10 to between 20 and 100 meg every time. If you look, matter of fact, if you look on GitHub, there's a bug I put in. One of the people there found an alternate data source that would blow up equally well, and it blows up reliably in at the tens of megabytes range, doing a read, basically the F read, something between F read and mem copy from the F read into the main memory into decode into whatever your buffer is supposed to be. It blows up and gets an unaligned read.
Thank you.
If you want, I could find you that. If you go into Raku GitHub and just look me up,
Yeah,
there
exactly.
are a couple of
Exactly.
bugs. That's one of them.
If I can't find it, I'll hit you up.
Feel free.
Thank you.
Anyone else?
Sure. So I want to know what the result was. Did you find duplicates? What kinds of things?
Yeah, there are always duplicates.
What-
Every time. What ends up happening to this stuff is, I can show you here. So we've got these. One thing I might actually give up doing is having one file handle per thread and actually have one file handle per chunk. Just open them as I go through. And the reason there is that sorting those small files is much faster. But what I end up having to do is sort these. I merge these by length and store basically either the nested hash from hell or an array by length with the nested hash from hell. And at that point, I can store counts. And after I'm done with all of it, you dump out I have all of the digests that came up more than once. I have to go back to the record numbers, and then I go back to the sequences for those record numbers, and I compare those as complete strings because they have the same length and the same digest. And even then, there will be multiple collisions that are unique. But the last time I ran this, I think I found 2 collisions.
And the response when you reported that?
Oh, we'll look into it. The people I think they don't like getting email from me. It's whoever deals with it. They always get I always get the same response. Oh no, it's unique. And I say, but wait, if you look at this one, record number this, record number that, begins with this, begins with that. Here are the two sequences. You'll notice they're identical. Oh, the response is always oops. And you know, I think they do all of this by selecting out of a large enough database. I don't know what procedure they use for it. The problem you get into is if you try to even do something as simple as shoving this up Postgres, just the raw database is so huge that you can get errors. So processing this is the fact that they can process it is pretty damn amazing. But yeah, I usually do find some dupes. Was this useful to people? I don't know if that's a yes.
Can I ask a question?
Sure.
Yeah. The one of the complaints about Raku is its speed, but you're using it for data-intensive purposes. Is there nothing? I mean, is there no other program that is faster?
I could use Pro 5, and Pro 5 might be a little faster. Even if I hack this in C,
So basically what I'm saying is, you know, Raku...
It wouldn't be much faster if I hacked it in C.
Raku is still as fast as anything else.
It's pretty reasonable. Well, my usual measure is this. If I look at XZCat, which is down around 63% right now, you can see this has grown to 28 gig, by the way. If I wrote this, the version of this that I have running in Perl 5 is slower because it doesn't handle the threading as gratefully. It uses forks and IPC and data pipes for all of it. So doing this in Perl 5 is a lot of work, and you spend enough time synchronizing things that eats into the... If I did this in C and threaded it, if you look at it, doing it, the code, do an index, read a buffer, append a buffer is not complicated. But the amount of work I would do in C to synchronize all the threads and create them and walk down the pool and find the next one that's available and feed the data into that thread and make sure, you know, lock the buffer, copy the buffer, unlock the buffer, start the thread. All of that overhead is there no matter what. And the IPC, if I run XZCat and I have the Raku program rating just reading, I can get XZCat up to 90-something%. If I type XZCat into cat greater than dev null, it doesn't get much above 95% because of IPC overhead. I mean, you're feeding things through a pipe. That's a kernel call. The kernel has to buffer it and then turn off one process and turn on another and fill some buffers and file handles. But yeah, I think there probably might be something out there faster than Raku that I could do it in. But frankly, by the time I was done writing it, compared to, you know, this much, which one would you rather write? I mean, I can process the input of this thing with one lazy gather right here. One lazy gather on a loop is everything it takes me to stage the data for n-way input. One race with a map is all it takes me to get this done n-way parallel with all the thread management done for me. Throw in the backslash, throw in the sync. You know, that's as much code as it takes to parallel process an arbitrary reader and n arbitrary handlers. So maybe I could do this in C, but how much time would I spend writing it, let alone debugging it? And like I said, if you watch this now, it does a pretty good job. You know, XZCat is moving. Since I kicked this off a few minutes ago, we've done 17 million sequences, 500, and so we're up to, you know, 9.2 gigabytes of data that have been processed through it, generating a digest for each and spitting the lines out. The files that are running here. Okay. I mean, there's a fair amount of work. Each one of these has got 500,000 records in it. And for each one of those, I had to read it, split out the string, strip out the new lines, compute a digest, and then spit one copy of it out here and spit the other one, spit the sequence out to another file. Now, the great thing about atomic ints is that all 42 threads are using the same dollar variable to increment their thread counter, excuse me, the sequence counter. And I don't have to write any of the synchronization code for it because it's all done in assembly as atomic process. So no, I think, I don't know if I were going to try and run the Nielsen system on Raku quite yet. But much like Perl, I think its capacity for processing data may be a bit underrated. It's gotten faster.
Looks like Vadim might have a question. I don't know if I pronounced
Yeah.
that right.
Yes, Vadim, correct. Not a question, but rather a note. Steve, I think you have a little bit of problem. You rely on thread ID to store file handles, as far as I remember. It's not reliable, unfortunately. I have bad news for you. Thread ID is not guaranteed to stay the same for a chunk of code, because over time, after some awaiting operations, like,
It doesn't
await
have
itself.
The file handle isn't specific to the chunk of code. The
Okay,
file handle
then
is
it's not a
specific to
problem.
the thread ID.
But for anybody else who doesn't know the specific, so keep in mind that Raku actually manages threads. And
Yeah.
at any time, your code could be relocated from one thread to another. So thread ID might
Sure.
change inside your code at some point.
But
That's
I still
it.
wouldn't have, well, the thread ID would change during one iteration of the loop.
No, I don't think so. It has to be
Then I
some
don't
kind
care.
of operation which actually releases thread resources. Like, again, like a wait or maybe read from channel. I don't remember all the details. I mean, I'm not
The
much
way
into the thread code, but
looking at it, what I was told, and if it's wrong, that's good to know now before I shoot my feet off, is right up here. There we go. So what happens is I go into process chunk. I know that this thread ID is supposed to be stable through one iteration. The thread ID shouldn't be changing through
within
one
one
call to
iteration, yes, no worries about it.
So the thread ID here, all I'm saying is for this one iteration of the code, I'm going to be in one thread until that call from map returns. The next time I enter this, whatever the thread ID is, there will never be two threads with the same ID. So I grab some file handles, I output everything for the chunk, and I return. To the best of my knowledge, if I'm using race, once I've dispatched that block into a thread, the thread won't change until the block returns. Because then it's idle. Now there's no telling which will be the next thread that gets called with the next chunk. I'm perfectly comfortable with that, because whenever it comes in here, it'll figure out which thread it is. It'll find the file handles for that specific thread, and it'll output to them until it exits and returns back in, and the thread is idle. I think that's supposed to be the way it works. Warn me if I'm wrong.
Unless you do something in atomic ink fetch, which might put your thread on hold, like if inside atomic ink fetch you do any reading from the file, there could be some waiting for data synchronicity, and at that point it is possible that it would happen. But on the other hand, when you enter this block, you most likely will have unique ID, and because you store it, you pre-store it, then it's okay.
Yeah,
You use pre-stored.
I assign it at the top of the block, and I keep using it throughout. Well, the other side of it is the lazy gather is called in map once to produce a chunk of data, and there's only one chunk that gets passed into here. I don't do any reading inside of the block. The only blocking operation I perform are these says, and they're actually putting out some pretty small chunks of data. So there are these two says into the two file handles that happen some number of times. I can't tell. But the read is done in the gather, because that's where that take grabs the chunk that was read, the next chunk that's been read out of the input stream.
We have a little under 5 minutes to go, and you do have one more hand up.
Sure, whoever it is, just talk.
Can everybody hear me? Steve, I thought it was a great talk.
Thank you.
Got a couple of questions. I missed, unfortunately, the first minute or two, and I'm just wondering if this is a bit of a...
Right.
No, that's fine. I was just wondering if this is a bit of an artificial test you're doing, because you don't seem to be testing based upon organism or phylum or anything to that effect.
No, the nr.gz file is supposed to be a unique list of all the amino acid sequences known to NCBI. The BLAST header line for each of those is a list of every organism that is known to exhibit that sequence.
Okay, so are you doing a first pass to pull out everything under a particular organism and then checking all those sequences?
I don't care. No. My only question is the non-redundant file redundant?
Okay.
If I look at all 128 million sequences in that file, are any of the sequences repeated?
Well, you're a very ambitious person if you want to do that. I mean, and
I usually
I think there are other ways. There are other ways you might want to approach it. But I mean, if that's your test, I thought your code was beautiful. I put in the comment section here. I'm sorry.
I'm doing it for the hell of it. I'm doing it. It's a non-trivial computing problem to try and determine the quality control. Is that much data in that cruddy of a format unique? That's it. Most of the time when I run it, I do get dupes and I send them back. I'll send something back to the nice people at NCBI with, I read the file published on this date and sequences number X and Y and Z were duplicated. Here's the sequence for this one. Here's the sequence for that one. Here's the first two organisms there. Here's the first two organisms there. And they'll usually say, oops, our bad. And they twiddle whatever bits in their database. And I usually don't see in the same sequences that are duplicated, but it's different sequences that are duplicated each time. I think what's happening is some of these sequences, they're selecting them by organism. And some of the time the sequences in the database are not unique, but they're given separate identifiers by mistake.
Absolutely. Or
so
they're
what
coming
I'm really
from a
doing
different
is helping them
genome
go back and find out which of their identifiers are incorrect.
They're coming from a different genome center and they're just aggregating them together and they're all getting thrown in together. So yeah.
But that's the quality control. This is a layer of quality control that if every time I find this, if you're trying to do this by organism, I'm saving you from not realizing that 16 dozen organisms really do share a sequence, because they've accidentally split two sets of organisms onto different editions of an identical sequence. That's where I got involved in this. Was I was working for a bioinformatics company, and that was our job, was giving people, it was for disease discovery, and people would look in the database and say, I want to find everything everywhere that has this amino acid. And if the NCBI data has dupes in it, and you look at the wrong amino acid, you're going to find half of them, because half of them would be associated with one entry and half with the other, and they really should all be collapsed into one. And it is a non-trivial problem. And if you look at the number of entries that it takes here, doing it in reasonable time isn't easy. And I had a solution that worked in Perl 5, which was similar to this one, but it was a lot more work to program and make it work properly. And the interesting thing to me in Raku is I could get the same amount of threading and everything else done with a hell of a lot less code.
So are you just doing this on a desktop or a workstation? Have you tried something like AWS or anything to that effect?
I've got well, what I've got in the next room screaming at me is a 4 CPU super micro server with 48 cores on it and 128 gig of core. That's why I can get, that's why the fact that if I didn't have, well, where is it? There's top. If I didn't have that much memory, this thing being at 36 gig resident would be causing me pain.
Okay.
But it doesn't even bother me until it gets up to 100 gig of resident. And I've got 128 gig of swap. And from what I've seen, once the stuff gets swapped, it never gets touched again, which is why I think it's a memory leak in More or in Raku. Because something somewhere is just not freeing something. But I've got so much memory, I can get away with it.
Nice.
You know, if I were processing this data for real-time telemetry at NASA to try and keep people from dying on the space station, I probably wouldn't be doing it in Raku. But neither are they, so no one's going to hurt me for it. But for this kind of a problem, it seems it's a nice, I think it's a nice solution because it's only this much code to make it happen. I mean, there is a perfectly generic single reader, multi-threaded writer, processor, handler for anyone, anywhere. That's as much code as it takes. If you tried to write this in C++, you could spend the next 6 years debugging the threading. So, like I said, you know, I started with the subscriber model. I tried the subscribers, I tried the channels, and then, I got, someone was kind enough to show me how lazy gathers in loops work. And from there, I just went down this rabbit hole. But this page right here is a perfect, this is completely generic. Anything, whatever your next chunk of data is, and whatever your process a chunk of data is, this is the framework that will do them in n-way parallel.